So now that we have a mathematical model, we have to figure out what this actually means in terms of the structure of the protein and how the structure of the protein is conferring this function. And so we can think of this in one of two ways from the math. We can either think of this as the concerted model, which is shown here on the left, or the sequential model, which is shown here on the right. Now, to understand these two models, what we need to think about is that the subunits, each of the subunits in the tetramer, can behave in one of two ways. Either they can have a low O2 binding affinity, so those are denoted by the circles in these diagrams. So this is low affinity. And to put a number on it, we'll say that the P50 for this is equal to 400 torr. Whereas the triangle, excuse me, the square, not the triangle, is high affinity. And so we can think of this as having a P50 of 4 torr. And remember, the lower the value of the P50, the tighter the binding of the oxygen, right? So what the concerted model says is that when ligand binds to one of these subunits, this promotes conversion of all of the subunits within hemoglobin to a high affinity state. So that means the more ligands that are binding to the subunits, the more likely all of the subunits are going to convert into some sort of high affinity O2 binding state. And that's going to cause the sigmoidal behavior. So this red arrow means that the equilibrium starts getting pushed further and further to the right. The more oxygen is bound to each, the more oxygen is bound, or the more subunits have oxygen bound to them, okay? And that will push this towards these high affinity sites shown here on the right. So this is sort of an all or none. So either all subunits are low affinity, or all subunits are high affinity. That's what this model says. In a sequential model, not all the subunits have to be high or low affinity. Okay? So there are different equilibria. So binding to a ligand promotes formation or promotes conversion of neighboring subunits to a high affinity state, but it doesn't have to be an all or none. So that's the only difference between these two models. Now the important key aspect of this is that what this implies is that there has to be some sort of way of communicating. Because remember, we know that the ligand binding site is not responsible for the different functions between myoglobin and hemoglobin. So that must mean it's something about the tetramer. It's something about having a tetramer versus a monomer. And what that something is that the subunits are able to talk to each other. And while one subunit, for instance, is able to, if one subunit is able to bind oxygen, which I'll show as red, it's able to communicate that information to the other subunits in some way. And so the question then is, how does it do that? Why does the tetramer promote this, but the monomer doesn't?